Hello students, welcome to EPD Pathshala. I am Reema Gupta from University of Delhi and today we are going to talk on module Structural Theories of Glass Formation, and this module is under the paper Ceramics. So after the completion of this module, you all should be able to know about the structural theories of glass formation, Goldschmidt's radius ratio criteria, Zachariasen criteria for glass formation, and various other criteria like Smeckel, Stanworth, Dietzel, and Son. So before moving further, let's introduce some basics. As mentioned in previous modules, the question why some materials form glasses and other do not has intrigued the scientist for many years. Before the idea of kinetic theory of glass formation were born, the ability to form glass by oxides, which were the earliest known glass formers, was discussed in terms of structural theories. So in this module, we will be describing various theories which can tell the structure of glasses. These theories are important in themselves as they have formed the basis of understanding the glass structure. The first idea regarding the ability of oxides to form glasses were from Zachariasen. So before starting with this theory, it is necessary to understand the Goldschmidt's radius ratio criteria for the formation of oxide crystal structures. So we will be first discussing the Goldschmidt's radius ratio criteria and then we will be discussing about Zachariasen criteria. Now let us first discuss about Pauli's rule for ionic crystal structure. So before considering the Goldschmidt's radius ratio criteria, it would be appropriate to consider briefly Pauli's rule on grouping of atoms in crystal with largely ionic bonding. So if the ionic crystal having predominantly ionic bonding, the energy can be minimized if the cations and the anions are packed relative to each other in such a way that the electrostatic attractive energy is maximized and the repulsive energy is minimized. Pauli has made certain generalizations which predict the majority of the known ionic crystal structures, and these generalizations have come to be known as Pauli's rule. So according to the first Pauli's rule, the anion surrounds each cation to form an anion polyhedron. The cation-ion radius is the sum of their radii. Here, one should understand that the concept of the radius of an ion is strictly empirical. The justification for this concept is that using these values, the interatomic or we can say interionic distances between the crystals can be predicted within a few % using a self-consistent set of ionic radii. A set of ionic radii is to be used for different coordination numbers. The anions are therefore assumed to be touching the cations and the number of anions surrounding the cation is called the coordination number. This number depends on the ratio of the radius of the cation to the radius of the anion. Now let us take an example. Consider a coordination number of 3, that is 3 anions forming a triangle with the cation sitting at the center of the triangle. This can be seen in the figure shown on the left hand side. That is, there are 3 anions forming a triangle with the cation sitting at the center of triangle. For the cation to touch the anion, the radius ratio must be larger than a critical value which is shown in the figure. So, in this figure, figure A shows that the Rc by Ra is just sufficient for the cation to touch all the anions. Figure B, Rc by Ra is larger than that in case A, where the cations continues to touch all the anions. Case C, Rc by Ra is smaller than the critical value and the cation cannot touch the anion. The values of the critical radius ratios for the different coordination number in this following table. So you can see that for different coordination number, the critical radius ratio changes. So for example, if we talk about the coordination number 8, the deposition of the anions around the cation is cube corners, for which the critical radius ratio is greater than equal to 0.732. So, the radius ratio places an upper limit on the coordination number of the cation. Thus, for a radius ratio of 0.4, the coordination number cannot be more than 4, as you can see from this table. It is possible to have a smaller coordination number than this upper limit, but the energy of the resulting configuration will be higher. It can be reduced by increasing the coordination to maximum permitted because the electrostatic energy of an array is decreased as a larger number of oppositely charged ions are brought in contact. It should also be noted that sometimes it is possible to have a higher coordination number than permitted by the radius ratio. In this case, for the ions to touch the central cation, some deformation of the ions will be necessary. This would increase the energy of the configuration. However, if the cation is highly charged, then the reduction in the electrostatic energy due to increased number of anions surrounding the cation may be sufficient to compensate for this increase in energy. Now comes the second rule of Pauli. The second rule of Pauli concerns the electrical neutrality. The structure must be neutral not only on the macroscopic scale but also at the atomic level. In a structure, a cation may be surrounded by anions having different charges. Thus, in Al2O3, for example, the Al3 plus is surrounded by 6 of O2 minus, while in kaolinite it is surrounded by 4 OH minus and 3 O2 minus. It is therefore not straightforward to determine if the electrical neutrality condition is satisfied. So, to determine if the requirement of electrical neutrality is satisfied in a case, the concept of bond strength is introduced. The strength of an ionic bond donated from an anion to a cation is defined as the formal charge on the cation divided by its coordination number. So, its bond strength will become 4 by 4. That is equal to 1. So, if we take the example for SiO2, the bond strength is charge on Si4 plus divided by coordination number of the silicon, which is equal to 4 divided by 4, which is equal to 1. It should be noted that in the above definition, only the number of anions surrounding the cations is counted. It does not matter if they are different. So the second rule of Pauling states that in a stable structure, the total strength of the bonds reaching from all the anions surrounding the cations must be equal to the charge on the cation. So there are some other criteria for glass formation. One of these are Smeckel. So Smeckel proposed that for glass formation, the bonding in material should neither fully ionic nor fully covalent, but should be of mixed nature. So the covalent bonds are highly directional and have rigid bond angles. A purely covalent bonding therefore cannot produce a random network structure characteristics of the glass. On the other hand, the ionic bonds are not directional and are incapable of forming a network. So the bonding in a glass must therefore be of mixed character. Now we come back to Goldschmidt's radius ratio criteria for glass formation. Goldschmidt observed that the oxides of the type ANOM forms a glass most easily when the radius ratio of the cation to ion, that is oxygen, Ra by Ro, is between 0.2 to 0.4. In organic compounds, this ratio determines the structure of the oxide. A radius ratio between 0.2 to 0.4 implies that the structure consists of tetrahedral coordination with 4 anions surrounding each other. On this basis, Goldschmidt came to the conclusion that only those metals which contained tetrahedrally coordinated oxygen formed glass on cooling. So this conclusion was purely empirical. Although largely true, there are many exceptions. Thus, 9TeO PbO form glass, but the coordination of Te is 6. On the other hand, if we talk about BeO with Rbe by Ro, which is 0.2 to 1, does not form a glass. This should also be noted that the bonding is not purely ionic in the glass forming oxides, while the radius ratio rule is derived for the ionic bonds. Now the next idea on glass formation came from Zachariasen. The Zachariasen ideas were addressed to the question of glass formation, but they became the foundation on which the models of glass structure were subsequently built and form an important milestone in the glass science. Zachariasen's idea grew out of his observation that the silicate crystals which radially forms glasses on melting and cooling have a three-dimensional network structure. Since the density and the mechanical properties of the glass and the crystalline forms are similar, it occurred to Zachariasen that the glass must also have a three-dimensional network structure, but the networks are not symmetrical and periodic as in crystals. The ability to form a network was therefore the criteria he proposed to predict whether an oxide would form a glass or not. So Zachariasen then considered the structural arrangements that would be necessary to form a network structure. Based on this, he proposed that the glass formation may occur in an oxide if the following conditions are met. So the first condition was each oxygen ion should be linked to not more than 2 cations. Otherwise, the linkage distortion to give a random network structure would not be possible. Also, there is a need to keep the cation as far as possible. The second condition is the coordination number of the oxygen ions about the glass forming cation must be small, 4 or less. Otherwise, an octahedral or cubic unit will result with no flexibility. The third condition was the oxygen polyhedra must share corners with each other, not the edges or the faces, just to keep the cations as far apart as possible. Now, the fourth one was at least 3 corners of a polyhedron must be shared, which is necessary to form a network. Now, let us take some examples for Zachariasen's rule. So, the first example is SiO2, that is silicon dioxide, or we call it as silica. For this case, the radius ratio is given as R of Si4 plus divided by radius of Ro minus, which is equal to 0.4 divided by 1.4, which comes out to be 0.24. So, this is corresponding to tetrahedral coordination. So, you can see that the number which arises, you can see in the previous slides, this corresponds to tetrahedral. So, SiO2 prefers tetrahedral bonding and so satisfied Zachariasen's condition number 2. Next, we find the coordination number for oxygen. This is done by using the condition that the ratio of the charge to coordination number should be same for both the ions. That is, charge of Si4 plus to Cn of Si4 plus is equal to 4 by 4, which is equal to charge of O2 minus divided by Cn, that is coordination number of O2 minus is equal to 2 divided by coordination of O2 minus. So we get that the coordination number of O2 minus is 2. This satisfied the condition number 1 of Zachariasen. Thus, SiO4 is tetrahedra linked at the corners, which will form a glass. Based on these rules, Zachariasen predicted that the following oxides should form a glass. And some of the examples are Ba2O3, SiO2, GO2, P2O4, As2O3, and so on. Out of some, only the few can made into glass under ordinary conditions. Moreover, in addition, subsequently, the following oxides have also been prepared in the glass form, which are indium oxide, that is In2O3, tellurium oxide, which is Tl2O3, tin oxide, SnO2, lead oxide, PbO2, and silurium oxide, that is SeO2. It should be noted that Zachariasen only proposed that an oxide may form a glass if certain conditions are met. He proposed the random network based on the similarity of the structure and the internal energy between the crystalline and glassy form of the oxides. Although proposed as a test for the glass forming ability. These ideas have become the basis for the glass structure, which we will be discussing later on. According to Smeckel, this requirement can be met in the following materials. So first are inorganic compounds in which the bonding is partially covalent and partially ionic. And the examples are silicon dioxide, that is SiO2 and B2O3. Second class is elements such as sulfur, selenium, which have a chain structure. The bonding within the chain is by covalent bonds, but the chains are held together by van der Waals bonds. The third class is of polymers. Polymers with large molecular chains are considered. Here again, the bonding between the chain is by covalent bonds, but the chains are held together by van der Waals bonds. Now, taking this idea further, Stanworth grouped the oxides into 3 groups on the basis of electronegativity of the cation. Since the anion is oxygen in all the cases, the electronegativity of the cation is a measure of the ionic character of the bond. Higher electronegativity implies lower ionic character. So students, you can see from this table that the group of elements are characterized on the basis of their electronegativity. You can see that in group 1, the compounds which are included are boron, silicon, phosphorus, arsenic and antimony. Whereas group 2 consists of beryllium, aluminium, titanium, zirconium and tin. The group 3 consists of magnesium, calcium, strontium, barium, lithium, sodium and potassium. So we have seen that there are 3 groups. So cations in group 1 form bonds with oxygen with ionic character greater than 50%. They should be network formers and should form glass by themselves. So they are known as network formers. The second group, the cations in group 2 have a slightly lowered electronegativity. They cannot form glass by themselves but can replace some cations in group 1. So they are known as intermediates. Group 3. The cations in group 3 with still lower electronegativity form highly ionic bonds with oxygen. They cannot form network. They can act only as network modifiers if added to the network forming oxides. So these oxides are called modifiers. Now here comes another idea which consider the case of glass forming, that is Dietzel. Dietzel considered the direct Coulombic attraction between the cations and the anions. This attractive force is equal to Ze of cation times Ze of anion divided by Rc plus Ra whole square. Here Zc and Za are the numbers of charges on the cation and anion respectively. Rc and Ra are the radii of the cation and anion respectively, and E is the electronic charge. For oxides where Za is fixed at 2, if Rc and Ra is equal to capital R, then Dietzel defined the field strength is given as Fs, which is equal to Zc by r square, where Zc is the number of charges on the cation. A high field strength implies a high attractive energy between the cation and the anion. Based on the empirical observation, Dietzel related the field strength to the ability of glass formation. He proposed that for glass formers, the field strength is greater than 1.3, whereas for intermediates, the field strength is between 0.4 and 0.3. And for modifiers, the field strength is less than 0.4. Now, considering the another idea which is given by Sun. Sun considered in a similar manner the single bond strength of the oxides as a criteria for glass formation. He defined the single bond strength as the dissociation energy of the oxide divided by the coordination number of the cation. He then proposed that if the single bond strength is high and greater than 80 kilocalories per bond, then the element is a glass former. Whereas if the single bond strength is between 60 to 80 kilocalories per bond, then the element is intermediate. Whereas if single bond strength is less than 60 kilocalorie per bond, then the element is a modifier. These various models have helped in determining the ability of an oxide to form a glass and so are useful. In particular, the random network model of glass described by Zachariasen is still the general picture of the structure of oxide glasses. However, as we have already seen in previous slides, as far as the ability of glass formation is considered, the kinetic considerations for preventing crystallization during cooling are more important. So students, let's now summarize what we have learned in this module. So we understood that the earliest known glasses were the oxides, and the question as to why some oxides form a glass and others did not intrigued the scientist, and the scientist looked at the structure of crystalline form of oxides to discover the correlation between the glass forming ability and the structure. So the first idea about the glass forming ability was proposed by Goldschmidt. So he observed that those oxides which had a radius ratio of cation to anion between 0.2 and 0.4 formed a glass most easily. This radius ratio implied that the oxygen should be tetrahedrally coordinated around the cations according to the Pauling rules. So Goldschmidt therefore proposed that for forming a glass, the oxide should be tetrahedrally coordinated in the structure of the corresponding oxide. Although largely true, there are many exceptions. So the next idea on glass formation came from Zachariasen. So Zachariasen's idea subsequently became the foundation on which the models of the glass structure were built and form an important milestone in the glass science. Zachariasen observed that the silicate crystals which readily form glasses have a three-dimensional network structure. Since the ability and the mechanical properties of the glass and the crystalline forms are similar, it occurred to Zachariasen that the glass must also have a three-dimensional network structure, and the networks are not symmetrically and periodic as in crystals. So the ability to form a network was therefore the criteria he proposed to predict whether an oxide would form a glass or not. Based on this, he proposed several rules to determine whether an oxide will form a glass or not. He then proposed a random network model of glass which has stood the test of time. It should be noted that there are some exceptions to the Zachariasen rules also, but his idea became the basis of subsequent understanding for the glass formation. Various other models like Schmeckel, Dietzel and Sun, they have proposed the structure. Schmeckel proposed that for glass formation, the bonding in the material should neither fully ionic nor fully covalent but should be of mixed nature. Thank you.